Okay, yeah. Good morning again, everyone. It's been a long break. I hope everybody was able to rest. It was a spring break under lockdown, so nobody was able to enjoy the spring break as it should be. But anyway, I hope at least you got rested well. All right, so since it's been a long time, I will start with a reminder of what we are doing. Then chapter 9, we were estimating population parameters, okay? And here, from this time forward, from section 9.2 and forward, you're going to basically estimate population means, difference between two population means or population proportions, mostly these things. So population mean, because most of the time the hypothesis we have is about the mean of the random variable we have. We are interested in its mean. Most of the time we are interested in estimating its mean. So therefore, from this time forward in this chapter, we are going to focus on means, proportions, differences between means, and these three things basically. So we have a population, and in this we have seen in chapter 8 that we are collecting data samples from we have a sample which is composed of data points, and by this sample measurement our goal is to estimate the parameter that we're looking for, estimate the population mean, for example. And we have seen method of moments, method of maximum likelihood, and most of the time when we have, for example, when we estimate the population mean, we just take the average of the samples we have. When the number of data points when the sample size is large, because of the central limit theorem, the population mean, the sample mean, is an unbiased estimator. It's basically uh, it's normally distributed. And in the first section, we talked about finding those parameters. Like, for example, X bar, sample mean, is a good estimator for population mean. Now, instead of getting a single value, the idea of confidence interval and hypothesis testing is that based on that sample size and based on the standard error of your estimator. This is very important. The standard error of your estimator, in other words, what is the standard deviation of your estimator? You collected X bar here for this sample, but if you computed X bar for a different sample, how much would it vary? Okay, this is the standard error of our estimator. Knowing, if we know this, if we have a way to compute the standard error, then by using the sample mean we have collected, we can also say how confident we are in this estimate of the sample mean. Because if it's too variable, the sample mean we have, for example, if you just collect a sample of size 10, and you just look at the average of that and to estimate population mean, that would mean basically if the standard error is too much, you would not trust your estimate that much, because if you get another sample of same size, sample of size 10, you're going to get something very different maybe. So standard error is a measure of how variable our estimator is. And we are going to see methods where the standard error is, our estimator is normally distributed, or if it's not normal, we are going to see another distribution, the student's t-distribution. But section 9.2 deals with the cases where we already know the population standard deviation. In other words, if we know, so we collected a sample with x1, x2, each of these xi's, so the sample size is n, each of these xi's are independently and identically distributed. And if we know the standard deviation of xi, okay, so if the population standard deviation is known, then if we want to estimate the mean, if we want to use x bar, the sample mean, as an estimate for mu, the x bar, its standard deviation, is going to be given as sigma divided by square root of n. So we have derived this formula because the summation is the variance of the summation is going to be n sigma square if each xi has a standard deviation of sigma. Because of the linearity of variance, the summation itself, the sum, is going to have the sum's variance. The variance of the sum is going to be equal to n times the variance of individual samples. And since x bar is the sum divided by n, so what we are going to have is that, so this is the variation of the sum. The standard deviation of the sum is going to be square root of n sigma, and the standard deviation of x bar is t dev x bar, which is this one. X bar is sum divided by n. Therefore, if we divide this by n, we get our formula for the standard deviation for our estimator. Okay, so this one also tells us that the average, your standard error, is going to decrease as sample size gets larger. And this is intuitive, right? If you collect more data points, if you have a larger sample size to estimate x bar, your standard error is going to decrease proportional to the square root of n. Okay, so it's not linearly decreasing as your sample size. So in other words, if you want to halve the standard error, you need to quadruple the sample size. Okay, so something like that. So it's basically, yeah, if you make it four times 4n, it's going to give you two. You're going to be dividing by 2 in that case. If you, yeah, exactly. If you increase the size, you use 4n here. 4 gets out of this as 2, so you will be reducing your standard error. So this is not the x bar. This is the standard deviation of the x bar. Okay, standard deviation of x bar is equal to this one. So this is how we when we know the standard error in our estimates, the general rule to have confidence intervals was basically the confidence interval, or our goal is to, instead of making a single estimate, we want to give an interval. For example, I have found out that the average is 3.4. Okay, x bar may be 3.4, but how good is this 3.4? So if you find x bar, for example, to be 3.4, the real mu, where is the how close is this x bar to the real mu? So what we do is that if this x bar is asymptotically normal, our sample is asymptotically normal, we standardize this. And another important property is that it has to be unbiased. So when we standardize this, x bar, expected value of x bar, divided by the standard deviation of x bar, makes this x bar a standard normal variable. We can look at the z table. This one will be equal to mu if it's an unbiased estimator. So there are certain properties in order to build these confidence intervals. There are certain properties our estimators should have. First of all, they need to be unbiased. If we have a biased estimator, we cannot build the confidence intervals by using the techniques we learn in this course. There may be advanced techniques, advanced topics of statistics that help you to build confidence intervals for unbiased estimators as well. But in this introductory course, we're just focusing on this general case where we have an unbiased estimator. So being this mu, when we standardize it, we see that instead of having this 3.4, by looking at the standard normal table, we can generate an interval around 3.4, okay, so that if so this 3.4, when it's standardized, basically 95% of the population, for example, if alpha is 0.05, if you want to uh, have a confidence interval with 95% confidence, what you do is you go, uh, so you basically, so the extend this 3.4 left and right with some margin. And this margin is the z value of alpha over 2 times the standard error, your standard error, okay? Whatever the standard error of your estimator is. If you go this margin to the right and left of z, and this z is our inverse CDF, which tells you that what is the z value, so that, for example, if you want to have alpha is 0.05, you want 0.025 of the population to lie here. This is like you accept to have this much error, 2.5% error. Here to this side, it may be so extreme that it may lie here, and 2.5% on this side. So this totals up to 5% of the population. So 95% of the population lies within this margin. So this z alpha over 2 is basically your inverse CDF. So you go that much standard errors away. So this is like non-standardizing your, if in the standard case, this will be 0, and this will be exactly z alpha over 2. When you non-standardize it, you move it to 3.4, and you multiply this z alpha over 2 with the standard error. So you go that much standard errors away from 3.4. And this alpha over 2, if you want to be very confident, for example, if you want to be 100% confident, your confidence interval is going to be between minus infinity and infinity, right? I mean, 100% if, because since normal distribution is the tails go all the way to infinity, basically it tells you that it's impossible to be 100%, exactly 100% confident. But you can be 99.9999 confident with not going too far, because this curve drops quickly to almost 0. So for example, if you go 4 standard errors away from the mean, not that much, 4 standard errors away from your mean, you would probably have something like this much confidence, okay? So that's a lot standard errors. So it drops quickly. So when I say from the confidence interval would be between minus infinity and infinity, it's just theoretically. Practically, the curve normal distribution is going to drop to 0 quickly after 4 standard errors, 4 standard deviations away from the mean. So this is our margin, and this is basically, instead of saying 3.4, we build a confidence interval around our estimate, where centered at our estimate. And this confidence interval, we say that it includes the real mu, real estimation, real population parameter mu. For example, if you're estimating mu, it includes the real mu with 95%, with 0.95 probability. Okay, so this confidence interval is something that is random, and it's the probability that this one contains mu is somewhere here. Mu is basically in a fixed position, and this is the slide for that. So as you can see, this theta is our mu, our population parameter. It's constant every time we get a new sample. So these are different samples we obtain. And each time we get a sample, we get a different confidence interval. The sample mean is at the center of these intervals, as you can see. And saying that with 0.95 or 95% confidence, our interval contains theta, means that if we collect, for example, 100 different samples like this, 95 of them is going to contain, 95 of those confidence intervals is going to contain the real population parameter. So this is what we did last time. This was a like 15-minute recap of what we have done last 2 weeks ago. Now, We also seen a generic methodology to construct confidence intervals, which I explained actually on GIMP here. First, our estimator has to be unbiased. Otherwise, we won't be able to put the actual population parameter in the equation here. In this equation, let me show you that again. You see in this equation, this is the critical part. I replace the expected value of x bar with mu. So the population parameter gets into this. And this is how I was able to say that population parameter is in this interval with this probability. So it has to be unbiased. It has to have a normal distribution. The estimator has a normal distribution. When we have large samples, for means, proportions, differences of means, our estimator is always going to be asymptotically normal for large samples. For small samples, if we have, if they're normally distributed, the individual variables are normally distributed. Even if we have a small sample, again, due to the linearity of expectation, our estimator is again going to be normally distributed. So we find the standard error of the estimator by using, again, techniques from linearity of expectation. If the population standard deviation is known, that's section 9.2. So there's a entire section 9.3, which is about the case where if we don't know the population standard deviation, what do we do? Okay, how do we estimate the standard error? What is our standard error? How do we compute that if we don't know that sigma for individual variables? That's the entire section 9.3. And we are going to see, again, a couple of cases. In large samples, we are going to use the sample standard deviation as an estimate for population standard deviation. So you're going to use an estimate to build a confidence interval for another estimate. But when the sample size is large, we can use the sample standard deviation to estimate sigma. And if the sample size is small, we will only look at the cases where we have normal distribution. And if we don't know the population standard deviation, in that case, we will not be able to use standard normal table, Z table. We'll see something else for that, the student's T distribution. Okay, so these, instead of obtaining this quantile Z alpha over 2, we will be looking at T alpha over 2 from the student's T table with a certain, there's another parameter there, the degree of freedom, which is depending, which we are going to see when we come to those, that distribution. So this is our X bar, for example, for population mean, we go Z alpha over, so, and this is the margin. So this Z alpha over 2 times the standard deviation of the estimate, which is the standard error. So this is our margin. So we go left and right with this margin amount around our estimate. This is the confidence interval. So as I said earlier, it may take some time to understand, to digest all this information in a couple of weeks, but if you solve examples, I think it will be clear. The classification of these different cases is not that difficult. There, as I said, there are only like a couple of cases where we have a large sample, known standard deviation, large sample, unknown standard deviation, small sample, normally distributed, but known standard deviation. We again use Z table there. We have a small sample, normally distributed, but if we don't know the population mean, we use the student's T table. If we have a small sample, but we don't know it's normally distributed or not, then we are not going to see any techniques to that. That's a difficult case. Small sample, non-normal distributed, we don't know anything about that. We are not going to see techniques in this course to solve that case. Now, yeah, if this is the easiest case, easiest example for confidence interval for population mean is mu x bar. So this is our estimator. X bar is our estimator. If the sample comes from normal distribution, then the estimator is also normal. If the sample doesn't come from normal distribution, X bar will be normally distributed due to central limit theorem if our sample size is large. It's unbiased. This is the standard error, as again I show on the slide. So all we do is X bar minus the alpha over 2 and the sigma divided by square root of n. So this one becomes a confidence interval for X1. We have we have gone over this example 9.13. Let me quickly go there. Confidence interval, yeah, 9.13. We had these 6 samples. It's known that it's normally known to be normally distributed. So the population standard deviation is given to us. So 2.2 divided by square root of 6 and 95% confidence interval, two-tail. In this confidence interval, we have both of the tails cut out with alpha over 2, which is 1.96 here. So we go 1.96 left and right, standard errors left and right of our sample mean, which is 6.5. So let's continue with more interesting other examples. For example, this is the case where we start to look at different things other than means. For example, what is the confidence interval for the difference between two means? These two means may be the average running time of your algorithm versus the average running time of the competing algorithm, which is the current state of the art. And your goal is, for example, to say that they are different, maybe. You have a hypothesis. We are going to see in hypothesis testing, we may have claim hypotheses saying that, for example, my algorithm's average is larger than this other algorithms, or running time is smaller than the other. You never claim your running time is larger than the other. So your running time should be small, right? So small running times are better. But we will compare two populations a lot. When we're comparing things, for example, Northern Europe people are taller than Southern Europeans. This may be, again, two populations, Northern Europeans, Southern Europeans. And that's two populations. And their height of this population, this is our two means. We can actually get an estimator for the difference between these two means. What is the difference between these two means? If the estimation is, for example, the estimate is 0, it means that they are not different. If it's a large number, the theta is something positive. This is Northern Europeans' height minus Southern Europeans' height. If we find the confidence interval and see that the confidence interval's left endpoint is even greater than 0, okay? So if it's something really positive, we may be confident that this hypothesis is true. We are going to tie the concept of confidence intervals is going to be tied to hypothesis testing in this manner. We are going to see. But we collect samples from these populations. If the population standard deviations are given to us, the sigma x and sigma y is known. We collect X bar and Y bar. This sample standard deviation and these sample standards variances, we are not going to need them if population variances are known. But if population variance is not known, when we collect large samples, we may be using this sample variance as our estimation for population variance. So here is how you build a confidence interval for the difference between two means. Our estimator that we propose is X bar minus Y bar, okay? You may say that, we could have chosen Y bar minus X bar, but no, without loss of generality, okay? So it's just depending on what you're looking for, and you should know which one is subtracted from the other, but this is basically the difference between population means. We are not using absolute value or anything. It's not the distance between population means. So population second population's mean is subtracted from the first population's mean. So this is our estimator. It's an unbiased estimator because of the linearity of expectation again. If each of these are unbiased, we know that x bar is unbiased. This is mu x minus mu y, which is what we are looking for. And the standard error here in this case, this is an interesting formula. Why is the difference of the standard error between two variables is a summation of the variances of these two things? Shouldn't it be the difference between the variances of these two things? Why do we have, although there is a negative here, why did it turn into plus? Again, if you, this is coming from, again, the linearity of expectation. If you go back to chapter 3 and look at that variance formula, this minus 1 here, what is the variance of minus y? So actually you could answer this really easily, intuitively. Look at this variable y. Okay, now I suggest a new variable, minus y. If the variance of this thing is sigma square, what is the variance of minus y? It should be something positive, right? It cannot be negative. It's also sigma square. If you look at the, if we have a constant here in front of this, so in other words, n times, if we have n times y, its variance is going to be, and the variance is going to be n square times the sigma square. So this is, let me quickly go, this is page 251. Let me quickly go here and show you, yeah, this one. Yeah, here it tells me if I have a, this is the variance of ax plus b. B is 0 in this case, okay? And it doesn't affect here. So this equation here, the variance of ax, if a is minus 1 there, we are going to have minus 1 square, which is 1, which means that the variance of minus x is equal to variance of x. That's why we have that in this on this slide. Let me go back to 251 quickly. Yeah, this is where we are right here. Confidence interval for the difference between two means. We can also take a look at the example there. But here, our estimator's variance, which is the standard error. Our standard error is going to be these two variances summed up and take the square root. In other words, we are going to have this formula inside the square root, population variance of x, population variance of y divided by the sample sizes, and take the square root of that. This becomes our standard error. So if this is the standard error, the idea is the same. So this was the estimate. Go z alpha over 2 standard errors to the left and to the right of your estimator. So the generic method is exactly the same. So let's take a look at an example before we go on to sample size versus margin. So this is the same thing from the slide. So we should have an example here. So this is the same formula. Yeah. Effect of an upgrade. So this is a nice example. A manager evaluates effectiveness of a major hardware upgrade by running a certain process 50 times before the upgrade and 50 times after it. So this is a controlled experiment where we have the same process is run before the upgrade 50 times, and the average running time is just like the example I gave, the running time of some algorithm you propose. Here we have a process that is running before the upgrade. Before the upgrade, it was running 8.5 minutes. And after the upgrade, on the average, it runs 7.2 minutes, in 7.2 minutes after the upgrade. And we collect this data, 8.5 and 7.2, by running the process 50 times. Okay, so this is our sample. And in both cases, the sample sizes are 50. And this is important. Look at this sentence. The following sentence here is giving us historically the standard deviation has been 1.8 minutes and presumably it has not changed. So this one is telling us, this statement is giving us something about the population standard deviation. This 1.8 here is not the standard deviation of this 58.5 running time. It's not the sample standard deviation, okay? If 50 could be considered large. By the way, you may ask, I mean, this is a very natural question when you say large sample, small sample, what is large? Okay, so it's really not a quantitative value. Large is something subjective. For example, is 10 large? Probably no, 10 is going to be considered a small number. So what is the threshold for small and large here? Usually 30, the sample size 30 may be a rule of thumb to consider. If it's less than 30 samples, it may be considered small. If it's larger than 30 samples, you may consider it large. And if it's 29, for example, it would probably not matter that much if you consider a small sample or a large sample. Okay, so at the boundary, the boundary between small and large is blurry. I mean, there is no, it doesn't change that much. Even if you consider 29 small sample and use student's t-distribution for unknown standard deviation, you will probably get a very similar confidence interval if you use the normal distribution table for that same 29 size sample, considering it as a large sample. Okay, but usually, as I said, 30 is a number that we can consider as the threshold for being large. So 50 times is therefore the sample size 50 is considered large here, but here we are not given the sample standard deviation. Okay, this 1.8 is the population standard deviation. So this sigma x and sigma y is given to us. The second part of the sentence, presumably it has not changed, basically tells you that you can assume 1.8 also as the standard deviation of the running times after the upgrade. So we just put everything that is given to us. So 90% confidence interval, we look at the alpha 0.05. So alpha over to 0.05. We go and look at the inverse CDF function, which is the z value, after which we have the, I mean, in other words, the area under the curve after the standard z value of 1.6. So 1.6 standard deviation after 0. That part is the area under the curve after that part is 0.05. This is basically telling us that in the standard normal table. So we are looking for the place where we have this is z alpha over 2, the area under 1 minus the CDF. Actually, we want 0.05. So we want this part to have an area of 0.5, which will give us this symmetric. Since normal distribution is symmetric, this is also 0.05. In other words, this is 90% of the population is in this interval. So this is z alpha over 2, which is 1.6, was it 1.645? Yeah, 1.645 is exactly this. A very good question. So how do we know that standard deviation is sample standard or population standard deviation? It has to be specified clearly in the question. Okay, so I mean, it's question statement. If the sentence is like, I mean, this is, I have some clues from here saying that if the standard deviation was given to me in the previous sentence saying that I have this 50 times measurement with 8.5 average and 1.8 standard deviation. If you state that 8.5 and 1.8 together for that sample, you understand that it's sample standard deviation. But in order to make it really clear, this question statement say that this 1.8 is not the standard deviation of the sample. It says historically the standard deviation has been 1.8 minutes. So it's the standard deviation is not specific to the sample. It's always been 1.8. So this is what it's trying to say. So from this clue, I understand that is population standard deviation. But you're right. Sometimes if the question statement does not state it clearly, there may be ambiguity. So this 1.8, is it the population or this are you referring to this sample standard deviation? So the question, whoever has written the question should make it really clear that it's either whether it's the sample standard deviation or the population standard deviation. For example, when it gives some general statements about the random variable we are interested in, it's the population standard deviation. For example, if you remember the previous example 9.13, it was saying that the standard the collection device or the measurement device, it was again saying the measurement device guarantees a standard deviation of this. So again, it's some general, it's not specific to the sample, it's a general statement about the measurement device. It's the therefore it's the population standard deviation. Okay, so it has to be stated in the question non-ambiguously, and here I can understand here it's not, this 1.8 is given in a different sentence than this sample information, and this historically keyword is a big clue for me that it's referring to the population. But as I said, it will not make a difference if the sample size is large. When our sample size is large, I mean, if this was, again, 50 is large, and if we understand it incorrectly and understand this 1.8 is the standard deviation of the sample in both cases, it wouldn't make any difference. We would exactly use the same technique. Instead of using sigma square here, we would be writing S, sample standard deviation there, and we will still use this Z table, okay, if we have large samples. The only case where it would matter is, I mean, where we would use a different table. T table is where we have small samples. When we have small samples and the standard deviation of the population is unknown, but the standard deviation of the sample is known, then we would not be using Z table in this case. Okay, that's the only case where the population and sample standard deviation would, the difference between them would matter. So yeah, we just, our estimator is the difference between these two means, which is 1.3. So 1.3 plus minus 0. You're welcome. 0.6 is our confidence interval. So this basically tells us that the confidence interval, so how do we interpret this? What does this mean? 0.8, 0.7, and 1.9. Since you subtracted, so X bar was the average running time before the upgrade, and this is Y bar is after the upgrade. So we want this theta being large is something good, right? I mean, because before the upgrade, we want it to reduce. So we want Y bar to be small. So we want this difference to be large to say that upgrade is successful. So when we build a confidence interval around 1.3, we say that we're 90% confident that the actual difference is between, I mean, again, I'm stating it incorrectly. The actual difference is something fixed, actually. It's not a random variable. Actual difference between population means. But I'm 90% confident that this interval here contains the actual difference, which means that the left end of this interval is positive. It means that upgrade probably is successful, but I'm 90% confident that this interval contains the actual difference, and 90% confident that the running time before is larger, because this is a positive number, and this is 0.7 larger. So you may then claim that the upgrade is successful. Okay. So the way he stated, the writer of the book stated, that we can say that the hardware upgrade resulted in a 1.3 reduction of the mean running time with a with a 90% confidence margin of 0.6 minutes. Okay, so 1.3 plus minus 0.6. It's the, you can also say that. Now, if we want to fix, or if you want to, for example, have select the sample size based on a fixed confidence interval. If you want to, for example, have a confidence interval around the mean for a fixed margin or for a fixed confidence is always fixed, but yeah, if you want to, for example, if I want to find out, so that's an interesting thing. For example, if you want to find the actual, not the actual, but if you want to be around plus minus 0.1 of the actual difference. Okay, so difference between two running times here in this case, when the sample size is 50, it's 0.6. Okay, if you want to decrease your margin and say that I want to, with the same confidence, maybe, okay, but with the same confidence, I want to decrease this margin. And the way to do that, to increase the sample size. If you increase the sample size, you can decrease this margin, because when you increase the sample size, standard error is going to get reduced. Another thing is, if you want to decrease the confidence interval here, you may decrease your confidence. If you, for example, if you want to be 70% confidence, the margin is going to decrease in that case. Okay, but with the same confidence level. If you don't want to change your confidence level but decrease this margin, the way to do that is to increase your sample size. So 9.24 is about this. Our margin, if you want our margin to be less than some delta, for example, if you want the margin to be less than 0.1, if you want to find our confidence interval with a margin less than 0.1, we want to be close to the actual thing. In other words, we have a given precision. That 0.1 margin becomes our precision. We want to estimate the actual difference with 0.1 precision. You don't want to go more than 0.1. The way to do that is just to change the way, since margin is equal to z alpha over 2 times the standard error. So this is our margin. We go plus minus this much. For a fixed z alpha over 2, we just take, so what we do is, if you want this margin to be less than that, we just take the sample size out. What should be the sample size? So we just fix the terms in this equation, left and right. We get margin here, this square root of n, we take the square root of the right hand side. So the sample size should be larger than this value, z alpha over 2 times your standard error of your estimator divided by the precision. So if you want to, for example, 0.6 reduced to 0.1 5 times, it means that you have to increase your sample size 25 times. Okay, so you see it's quadratically proportional to, if you want to decrease, if this delta is reduced 5-fold, it means that you have to increase n at least 25-fold. It says greater than or equal to. More samples doesn't hurt. Not more samples. Larger sample size does not hurt. But you have to be at least 25 times. Which means that, so 50 times 25 is your sample size should be that much if you want to find the difference between running times with 0.1 precision. So let's go, sample size versus margin. So this is our margin is the length, our estimator is so if you want to decrease the margin, we need to increase the sample size. If you want to increase the confidence level, again, we need to increase the sample size. Okay, so if increasing confidence level means that this d alpha over 2 is going to get increased. So this is section 9.3. I'm not going to start sigma is unknown case. I mean, I'm just going to solve this 9.5 today and call it a day. Let's 9.15, sorry. Let's look at 9.15. It's this one. It's a short example. Uh, so in 9.13, there was a 95% confidence interval with the center 6.5 and a margin 1. This was the margin based on a sample size of 6. Now that was too wide. So 1.76 around 6.5 is too large. If you want to uh, decrease it to 0.4 units with the same confidence, what should be the sample size? So 0.4, we write it here. So what we need to do is we could have also divide 1.76 by 0.74 to see how much the decrease is going to be, and then take its square root and find how much of a fold, how many folds our sample size has to increase. So that's the same thing basically, because these parts did not change in the previous case. They are the same. So this one is just was reduced from 1.76 to 0.04. So what I'm saying is that we could have done this where is my calculator? Oh, it's right here behind the chat. So 1.76 divided by 0.4, 4.4. Square that, 4.4. It's this. So it has to be this much. And our original sample size was 6. Multiply that with 6. We get exact same thing, 1.16.2. Okay, so if we have something like this, since this is not an integer number, we can round it. It has to be larger than 1.16. So we should at least get a sample size of 117. So 117, with 117 observations, you would have, with 95% confidence, you would be around, your margin is going to be 0.4 units between 6.5. Again, if 6.5 turns out to be the average of these 117 observations, of course. Probably with 117 observations, the 6.5 is also going to change. But whatever that is, if you go 0.4 to the left and right of that one, you will, the probability that the actual X bar is in this interval is going to be 0.95. Okay, so this is how, if you want to decrease your margin, which means increase your precision in your estimation, you have to increase your sample size, and it has to increase quadratically based on how much you want to decrease your margin. Okay, so I'm not going to start 9.3 today. I'm going to start 9.3 unknown standard deviation cases on Thursday. And good luck on your exam this evening, and see you all on Thursday. I will be happy to answer any questions if you have any, but if not, that's it for today. I will stop recording.